Welcome to Real Analysis Basics B2, Algebra of Sequence Limits. Today we turn the definition of convergence into a usable toolkit, because repeating epsilon and n forever is technically a lifestyle, but not an efficient one. Recall that an converges to a when, for every positive epsilon, all terms after some index n lie within epsilon of a. The important phrase is all terms after n. Convergence controls a whole tail, not a carefully selected collection of cooperative terms. Every result today is just this definition plus inequalities. Analysis will later acquire more machinery, but it never loses its enthusiasm for making inequalities do unpaid labor. First, a real sequence has at most one limit. This sounds reassuringly obvious. Unfortunately, real analysis accepts obvious facts only after they produce identification. Assume an converges to both L and M, and suppose L is not M. Choose epsilon to be 1/3 of the distance between L and M. For sufficiently large n, the same term an must be within epsilon of L and within epsilon of M. The triangle inequality now says the distance from L to M is less than 2 epsilon. But 2 epsilon is only 2/3 of that same positive distance. A positive number cannot be strictly smaller than 2/3 of itself. The assumption L not equal to M is impossible. Therefore the limit is unique. Second, every convergent real sequence is bounded. Convergence only promises control after some index. So we must also deal with the finitely many early terms. They do not vanish merely because textbooks prefer tails. Use epsilon equal to 1. Then beyond some n, the distance from an to L is less than 1. The triangle inequality gives absolute an less than absolute L plus 1, so the tail is bounded. Now let M be the maximum of the finitely many early absolute values and absolute L plus 1. Every term is bounded by M. The tail came from convergence. And the finite beginning was handled by taking a maximum. The converse is false. The sequence -1 to the n is bounded and still refuses to converge, alternating forever with admirable job security. Suppose an converges to a, bn converges to b, and c is a real constant. Then sums, differences, and constant multiples converge to the corresponding arithmetic combinations. Products converge to the product of the limits. Quotients converge to the quotient, provided b is not 0. This condition is not decorative. In fact, if b is non-zero, convergence forces bn to stay away from 0 eventually. So the quotient is eventually defined. We will prove the product rule. The sum, difference, constant multiple, reciprocal, and quotient rules are exercises. Assume an tends to a and bn tends to b. We must make the product error smaller than epsilon. Add and subtract an times b. This splits the error into two controllable pieces. Taking absolute values and using the triangle inequality gives this estimate. The previous theorem now earns its rent. Since an converges, it is bounded, so absolute an is at most some constant c. Given positive epsilon, choose n large enough that both of these inequalities hold whenever n is at least n. The harmless plus ones avoid dividing by 0 when c or absolute b happens to be 0. Analysis occasionally permits convenience. Substituting those bounds into the product estimate makes the first term smaller than epsilon over 2 and the second term smaller than epsilon over 2. Therefore the product error is smaller than epsilon for every sufficiently large n. Hence an/bn converges to ab. Limits preserve eventual non-strict inequalities. If an is at most bn eventually, then a is at most b. Proving this is an exercise. Assume A is larger than B. Then choose epsilon smaller than half their gap. Strict inequalities need not remain strict. 0 is less than 1 over n for every n. But both sequences converge to 0. The absolute value criterion says an converges to a exactly when the error sequence absolute a n-a converges to 0. This is another exercise. Unpack both definitions and compare the inequalities they require. There is no need to invent new machinery. The squeeze theorem says that if an is at most bn, which is at most cn eventually, and both outer sequences converge to L, then bn also converges to L. Geometrically, the two outer sequences close in on L, leaving the middle sequence nowhere else to go. The proof is an exercise. Translate both outer convergence statements into an eventual epsilon interval. Then trap bn inside the same interval. For example, sin n over n is trapped between -1 over n and 1 over n. So it converges to 0. Here are the promised exercises. Prove the sum and difference rules. Constant multiplication. Reciprocal and quotient rules. Order preservation. The absolute value criterion. And the squeeze theorem. You need only the definition of convergence, the triangle inequality, and the reverse triangle inequality. No new theorem is hiding under the desk. Do not merely cite arithmetic properties to prove arithmetic properties. Circular reasoning is extremely efficient, which is precisely why it proves nothing. We proved uniqueness, boundedness, and the product rule, and stated the remaining algebra, order, absolute value, and squeeze properties. Next, we study monotone sequences and subsequences, where order and completeness begin doing serious structural work. Until then, prove the exercises. Epsilon will not choose itself, despite years of students waiting patiently for that feature.